Okay, finally we managed it. Okay. Good evening. I'm Alessio Antonio. I'm product manager for Mitsubishi Electric Hydronics and Cooling Systems. The topic of this presentation is 4-pipe smart heat pumps. So units developed to produce at the same time cold water and hot water. The 4 topics of these presentations will be an in-depth view of the technical content of smart heat pumps, 4-pipe heat pumps, and why they are different from standard chiller and chiller with heat recovery. And then an additional technology for producing very high water temperatures. Okay? And then a quick overview on the Eco Design Directive and which is the impact on chillers and heat pumps and reversible heat pumps for sure and for pipe units. And then a case study to really understand the efficiency of the 4-pipe concept compared to a traditional system. So starting from the beginning, just a couple of words about 4-pipe system, 4-pipe plants. Well, in these years it is becoming more and more frequent that the building requires hot water and cold water at the same time. This is due to several reasons. For example, if we consider office buildings or in general multifunctional buildings, the modern architecture has large glazed surfaces, so solar heat gains can be really high also during the cold season. And each of us uses a PC and other machineries which produces heat, so internal heat gains are really huge also in the cold season. Moving to hotels, well, for sure, large hotels, especially in the middle season, we have some rooms facing to the north, while some others facing to the south. We have meeting rooms full with people, and other meeting rooms with solar heat gains due to a facade, for example. So it is frequent that in hotels I must supply hot water and cold water at the same time, and with different combination of load. For sure, when we move to industrial applications where we have a lot of examples of processes requiring heat in some part of the process and cooling in some other parts, for example, to cool down the machinery of the process, okay? So it is common. Remaining in the comfort, cooling, and heating application, this could be really a simplified thermal profiles of a multifunctional complex, okay? So we have cooling load, of course, lower during the cold season, and heating load as opposite, higher. And of course, during the summer season, it is the opposite. Okay. So, regarding hydronic plants, how to manage this kind of building? Well, we have 3 main possibilities. Okay, we have traditional plant, we have a heat recovery plant, and then we have the smart heat plant, 4-pipe plant. Okay. Traditional plant uses 2 completely different technologies to produce. One for producing cold water, typically a chiller, air-cooled, water-cooled, whatever, and a separate system, typically a gas boiler, to produce hot water. Okay. So 2 completely separated systems that works on their own. A step further is using a chiller with heat recovery. Chiller with heat recovery is a technology that allows to produce a certain amount of hot water while the chiller is producing cold water. So with the chiller with heat recovery, we are able to fulfill the building inside this yellow area here. So how it is possible? Let's have a look on partial heat recovery, for example, technology. Partial heat recovery technology has an additional exchanger placed after the compressor. Okay, and with this technology, we are able to recover a certain part of the superheating load. So while the chiller is producing cold water, we are able to recover a certain amount of hot water in an auxiliary circuit. And in this case, it is between 10 and 30%, more or less, it depends on the conditions, 10 and 30% of the compressor's cooling load. Okay. Second possibility, chiller with total heat recovery. In this case, we have an additional exchanger placed in parallel to the main condenser, so we are able to recover the total condensing thermal load, still with the chiller producing cold load, okay, cold water. in this case, the capacity recovered is the total cooling load of the compressor because we are diverting all the refrigerant flow inside this additional exchanger. So these two technologies are okay, are good, and allow us to have a certain production of hot water while we are producing cold water. So, okay for this part here, okay for all the part where the cooling load is higher or at least equal to the heating load. Because with this technology we are able to recover at least the maximum cooling load of the compressor. Okay. We are not able to fulfill these particular areas here. So even with the chiller with heat recovery, we still need a boiler. We still need an additional system to provide the heating when the heating load is higher than the cooling load. Okay, so chiller with heat recovery is okay and works alone inside this area here, but still needs an additional, an auxiliary system to work here because it is not enough. And this is why there is room enough for four-pipe units. In fact, a four-pipe unit is really a smart solution that doesn't need any additional equipment, any additional gas boilers, without any problems in terms of combining different thermal loads, whether the cooling is higher than the heating or the heating is higher than the cooling. And now we will have a closer look at why it is possible from a technical point of view. Okay. This is a simplified view again of the refrigerant circuits of a four-pipe unit. Okay. We have three main sections. We have a hot side heat exchanger, which is always the condenser. We have a cold side heat exchanger, which is the evaporator, and these two are connected, of course, to the four-pipe of the plant, hot pipes and cold pipes. And then the key part of the four-pipe unit is this auxiliary heat exchanger. This auxiliary heat exchanger, it can be an air coil or an additional water-to-water heat exchanger, depends on what type of unit it is. And it works either as a condenser or as an evaporator to exchange the remaining energy the building is requiring. Okay, now we have prepared a short video to better understand what is the working principles, to have a better view, let's say. So this is the same refrigerant circuit, okay? So, for example, if the building is requiring 100% of cooling capacity, like in this case, okay, the building in this condition is requiring only cooling capacity, total capacity. This means that both circuits, here we have two circuits, both compressors are running at their maximum capacity, using the evaporator to evaporate the refrigerant, all the refrigerant flow, okay? And then, as we are not requiring any hot water here at the condenser side, the auxiliary exchanger is used as a condenser to get rid of the heat I am removing here at the evaporator. Okay. In this case, so the function is like a standard chiller. Okay. In this case, air-to-water chiller. Then, as opposite, we can have the opposite condition. For example, the plant requiring only heating capacity. In this case, building again requiring heating capacity at 100% of the load. So in this case, the four-pipe unit is working like a heat pump. So as the building is requiring hot water, I must use the condenser at what percentage? Well, in this case, I am asking 100%, so both circuits are running at their maximum to produce hot water. No cooling capacity required, so I won't use the evaporator to produce cold water. And how to exchange the remaining energy? Well, I take from the ambient, from the source, the remaining energy I need to produce hot water. So in this case, the auxiliary exchanger is an evaporator and works as an evaporator, in this case air source, so gaining from the source the remaining energy I need. Okay, no problem with this. This is the standard chiller and heat pump model. There's no special things about it. But of course, 4-pipe unit must work in 4-pipe mode, so producing cold water and hot water at the same time. And this is the case. This is only to show you because this is a particular case. It is really difficult that in reality the building requires 100% and 100% on water surface. It is a very lucky situation, but just to have an idea on how the refrigerant circuit works. In this case, we are requiring total capacity in these circuits, so we are not using the auxiliary exchanger. We are condensing all the refrigerant inside the main condenser and evaporating all the refrigerant inside the main evaporator, producing hot water and cold water at the same time. Okay, this is a condition where a chiller with total heat recovery is okay. But the next combination is exactly the combination I was talking before. So a combination where the heating load is higher than the cooling load, which is the combination in which a chiller with heat recovery is not enough. And this is the point. For example, again, the plant in this case is requiring 100% of heating capacity, 50% of cooling capacity. In a chiller with total heat recovery, it can cope with this condition. A 4-pipe unit can, because, as you can see, 100% of capacity required. This means that both compressors must run at their maximum to produce hot water. So using the condenser of the plant, okay? And then half of the capacity is required at the evaporator level. So one circuit is using actually the evaporator to produce cold water, while the other uses the auxiliary exchanger to exchange the remaining energy with the source. And so in this case, it is an evaporator because heating load is higher than the cooling load. And so in this case, I am taking from the source, okay, half of the capacity I need at this point here. The real thing about this operating mode is the fact that when the building is requiring actually cold water and hot water at the same time, in this case, one of the two is for free, because with a single power input of the compressor to produce only hot water, actually I am producing also cold water, so we have two useful effects at the same time. And this is why the efficiency of this concept is really high. You see here, we cannot measure the efficiency of this particular unit with the standard parameters like ER or COP we use in chiller and heat pumps, because in this case we must take into account also the fact that we have two useful effects. So TER, total efficiency ratio, is the sum of heating capacity, cooling capacity divided by the power input. And in this case, can be really high, also over 8 in certain conditions. Okay, because we have two useful effects with one single power input. Of course, as the unit is able actually to manage all the combination of load, because this auxiliary exchanger can work either as an evaporator or as a condenser. So we don't have the limit of a chiller with total heat recovery in terms of combining the request of the building. Okay. Like already explained, the TR, total efficiency ratio, is the ratio between the sum of cooling capacity, thermal capacity divided by the power input. So just to resume the main advantages of using this solution, of course, in a 4-pipe building, so in a building that actually requires hot water and cold water at the same time, is the fact that the unit is more compact. We don't need the gas boilers, so of course we take less technical room. Okay. The system is simplified because we don't have to manage hydraulic inversion on plant, and we don't need all the stuff related to the boiler, so fuel lines, chimneys, and so on. And of course, also the management is simplified. Just to think about the maintenance relates to one single unit, which is a heat pump, basically. And the system is automatic. So you don't have to switch between summer and winter mode because every combination can be met. surely when we have a gas boiler, we have also domestic hot water requests. So the typical temperatures of a smart heat pump or a heat pump, standard heat pump is, I don't know, 45 to 50 degrees, more or less. So there are not enough for domestic hot water production. But there's another technology which works in cascade with the main 4-pipe unit, which allows to produce very hot water up to 78 degrees. So coupling with this additional water-to-water heat pump with the main 4-pipe unit, we are able to set a cascade system and deliver 3 independent thermal fluxes. So, for example, this could be an applications where we have comfort cooling, comfort heating, and also domestic hot water, laundry services, and so on. So typical for an hotel application, for example. How does this concept work? Well, as said, it is a cascade system, more or less. This means that we have this module here, which is an additional water-to-water heat pump with the special technology inside, of course. It takes part of the medium temperature hot water produced by the smart heat pump, the 4-pipe unit. Here we can have for 45 degrees, for example. This 45 degrees hot water is sent to the evaporator of this additional water-to-water heat pump. And so by evaporating higher, thanks to special technology inside, we are able to condense higher, and so to produce 78 degrees of hot water. And of course, the only limit in this case is the fact that as we are sending part of the medium temperature hot water here at the module, at the additional water-to-water heat pump, of course, here available for the building, I would not have the total heating capacity produced here, but of course, it is a matter of calculation. Okay, okay, this is the technical content of the 4-pipe unit and technologies for enhancing even more the temperatures on water side, hot water side. Cristiano made a good presentation regarding Eco Design Directive and its impact on air handling unit and recovery systems. Of course, Eco Design Directive have a strong impact also on hydraulic systems, so chillers and heat pumps. Okay. So there are just a couple of slides. I won't go so in detail about this because it is a very huge quantity of information. But just to have the key parameters of Eco Design Directive applied to chillers and heat pumps. Okay. So inside the directive regarding chillers and heat pumps, we have 3 regulations. The first one, the 813, uses the SCOP and is regarding heating systems. So systems that produces hot water, basically. Okay, and we have 2 tiers. The last tier entered into force the last September. Okay, setting minimum efficiency levels. One really important thing: each of these parameters are are considered as a seasonal efficiency, not full load efficiency, but seasonal efficiency. So the regulation stress the concept of high seasonal efficiency in the unit. Okay. So heating systems, the parameter to comply with is the SCOP. Okay, seasonal COP. If we are talking about the chiller, so a unit which produces cold water, we have 4 different parameters according to the applications. We have this regulation which covers SEER, so comfort cooling applications. So comfort cooling means I produce cold water for comfort cooling, for getting down the temperatures inside a building, okay, for air conditioning. In this case, as said, the parameter is SER, seasonal ER, and the first year will start the next January. And then we have a second tier in January 2021. Of course, the second tier is more demanding than the first one. Again, if we have not a comfort application, but we have a process cooling application, like an industry, for example, we have three main possibilities. It depends on the water temperature levels. So, if the temperature of the process cooling application is 7 degrees, or the regulation says between 2 and 12 degrees, but the standard condition to be considered for the calculation is 7. Okay, so we use the SCPR high temperature, which has the same time schedule of the comfort parameter. Okay, same time schedule. So again, the next January will enter into force both comfort cooling parameters and process cooling high temperature parameters. Then if we have a process that requires fluid at a lower temperature, -8 or -25, we must be compliant with these two parameters covered by this regulation, which is different from this one. We have -8, -25, and it will enter into force the second year, because the first year is active since two years ago, more or less, okay, in the next January again. So the next January we will have both comfort cooling and process cooling entering into force and setting high efficiency levels in terms of seasonal efficiency, part load efficiency. Okay. We know that for pipe units, or in general reversible heat pumps, actually they are able to produce hot water but also cold water, reversing the cycle. So what must they be compliant with? With the SCOP, because they are heat pumps, or with the SCR, because actually they are able to produce cold water? The regulation is not so clear in this point, but the key is this one. So if the reversible heat pump, or the 4-pipe unit, or every equipment that is able to produce cold water but also hot water, not in the same time or also in the same time, if this unit has a design capacity below 400 kilowatts, then it must be compliant with the SCOP. So the last year entered into force 3 weeks ago. Okay. What is the design power? Well, it is a different concept than the traditional design capacity, capacity of the heat pump, because we have three main parameters. We can choose the equivalent temperature. This means the temperature at which the heating capacity produced by the unit is equal to the heating load of the building. And the regulation said that the equivalent temperature must be below 2 degrees, but we can select them, okay? Then there are three choices in terms of climate. We have average with a design temperature of -10. We have a warmer climate, design temperature 2 degrees, and colder, -22 degrees. So again, an additional parameters which affects the design power. The last one, of course, probably the most important one, is the water temperature level. We have two possibilities: low temperature 35 degrees, medium temperature 55 degrees. So once we have selected these three parameters, we know the design power of our heat pump. If this design power is below 400 kilowatts, then must be compliant with the SCOP. And if it is higher than 400 kilowatts, well, it must be compliant with the parameters of a cooling-only unit. And it is not so fair, in our opinion, because a unit which is intended to produce hot water can be as efficient as a unit intended to produce only cold water. Okay, but this is the regulation, and we must be compliant with this one. So in this particular field of the market, so reversible units, this means heat pumps and 4-pipe units above 400 kilowatts of heating capacity at design condition, must be compliant, must have the same efficiency levels of a chiller. And it is quite tough. And we are talking about enlarging the surfaces using variable speed technologies, using additional device is to rise up the efficiency, because we have to take into consideration that reversible heat pumps have at least one four-way valve inside the refrigerant circuit. So this means additional pressure drops. Additional pressure drops means less efficiency. And so always the same method of efficiency in cooling only unit. Okay. And so this is the framework of the directive in a very few, in 2 slides, basically, just to give you the idea on how it applies to comfort cooling, process cooling, or heating. There isn't any difference between heating, comfort heating, or process heating. Only heating. So only the cooling has 4 different levels of temperature and 2 different applications, comfort and process. But heating, no. Okay, the last topic of this presentation is the case study. So let's focus on full pipe technology, and in this case study we will see real numbers associated with the real project in which we had the chance to compare traditional system for pipe unit. The project is this one. We are in London. It is quite a big building. We are talking about 7 stories and nearly 1,500 square meters each. So quite a big building. Okay. This was and still is a 4-pipe building. This means that originally they had 3 gas boilers for heating, 2 air-cooled chillers for cooling. So traditional system. A separate system for cooling and separate system for heating. And we carried out an energy analysis, a dynamic energy analysis with Transys software, taking into considerations, of course, the envelope of the building. So this means all the surfaces glazed or the opaque walls inside. We took into consideration the real orientation of the building, so all the shadows in the surrounding, and of course the effect on solar radiations, and of course also the people inside the building, heating load, internal heat gains of people inside. Okay, and so we carried out a dynamic energy analysis, and we found that this is actually the thermal profile of the building in 1 year period. So for most of the time you see that this particular building requires heating and cooling at the same time. Only for the few months during the summer the building is requiring only cooling. In particular, this is another interesting point, that as you can see, the cooling peak load is more or less double the heating peak load. So what was the best combination between units? Well, the result has been selecting a smart heat pump, a 4-pipe unit covering the maximum heating peak load. But the maximum heating peak load was more or less 500 kilowatts, so this means that the unit produces, again, more or less 500 kilowatts in terms of cooling capacity. Then, to get the extra cooling capacity needed, we sized an additional maglev chiller with magnetic bearing, oil-free. Okay, so this was the plan. We carried out our energy analysis considering the efficiency of this combination of plan. And this is just a general, very simple view of the plant. We have, of course, the 4-pipe unit connected both to the heating system and to the cooling system. The chiller is connected only to the cooling system, and then the tenants decided to keep the gas boilers as a backup, because the dismantling cost was really high and they were relatively new, so they decided to keep it as a backup. But as we later see in the results, they mostly never use it. Okay, so if the building is requiring at the same time hot water and cold water, of course, the system uses a 4-pipe unit. And in case if we have higher cooling capacity, then the system kicks in chiller. Okay. Of course, when the building requires only hot water, in the plant is running only the smart heat pump, and in case the backup boilers in case it is needed, for example, for very extreme low temperature in terms of air, okay, external air. And this is the case where the chiller, the plant is requiring only cooling capacity in the summer months, where we have only cooling load. We run the chiller and then the 4-pipe unit in cooling mode. Okay, and everything is managed through plant control with active optimization system, which takes into account the real efficiency of the unit, and which is the best combination of chiller, heat pump, and backup boilers. Okay. Okay, as said, we obtained from the simulation very good results, honestly, yes. But these are the real numbers after 1 year of operation, 1 year of monitoring the unit. This is not a simulation, these are real numbers. So, as you can see, it is true that this plant is requiring heating and cooling for most part of the year. Okay, as you can see, the blue line and the red line are cooling and heating demand. The gray line is the power, the energy consumption of the unit, and the green line is the energy which is recovered, let's say, for free. In the previous slides, we saw that when the system, the 4-pipe is producing hot water and cold water at the same time, we can consider that one of these useful effects is for free. And this is the meaning of this green line. So, okay, this is from the numbers in terms of power, cooling, heating, recovered energy. Really good, but these are the really interesting numbers. And these numbers are being calculated not by ourselves, but by the tenants of the building. We have a very huge gas consumption reduction, over 80%. This means that the gas boilers were never used in 1 year. And so this means that we have a very huge carbon dioxide emission reduction, over 2,000 tons each year of reduction. And most important, we cut the primary energy consumption by nearly a half than compared to the previous system, compared to a traditional system, which was an high efficiency, has an high efficiency chiller, okay, 3. And in the end, summing all these benefits at the end of the year, they calculated they are saving more or less 50,000 pounds. And so they made a calculation that these numbers here gives 1 year payback, more or less. So in this particular case, we obtained very good results with comparing 4-pipe technology to traditional technology. Very good results in terms of carbon dioxide, also emission reduction. The technology is quite plug and play, let's say. The installation has been just 7 hours during the night, so starting from the early morning, the tenants don't have any problems in terms of running the heat pumps. Okay, so good results. So in this case, in terms of inconvenience for the people inside. Like this, there are many others. Of course, this one is quite big, so it is interesting. But there are many others projects like this where we carried out the energy analysis and found that if the conditions of the surrounding are good for the applications, this is really a good technology. Okay, if you have questions, thank you.